day 4. Okay, because of the equal here, this is going to be a solid line. And because it's a less than, this will be below the graph. Okay, this line here will create the actual boundary between the two regions. The region under that line will be the ordered pairs that satisfy that inequality, and the region above the line will be all of the ordered pairs that satisfy that inequality. Okay, if you graph this using the intercept method, you know that y is going to be equal to -4. So I go down 1, 2, 3, 4. And I know that x is going to be equal to 1. So x is going to be 1. This is going to be a dashed line. So I'm going to do this. Now, here's the tricky part if you use standard form to graph this. Because the y is negative, we're not shading the part under the line, we're shading the part above the line. So the line on this side gets shaded. Okay, because the 4 and the 1 go into this 4 without a remainder, I'm going to graph this in standard form. Okay, so my y is equal to -1. And my x, oh, excuse me, -4. What am I doing? My y is equal to -4. And my x is equal to 1. And so when I graph this, I'm going to graph a dashed line because there's no equals. And I'm going to use a straight edge. Okay, because 4 and 1 go into this 4 without a remainder, I'm going to graph using standard form. So just looking at my x's, x is equal to 1. So I'm going to put a dot there. Okay, and then my y's, here, the y is equal to -4. So I'll put a dot there. And I'm going to graph this using a dash line because there's no equal sign. So I'll try and get a piece of graph paper here. And use a straight edge. And there's our line. Now be careful. We are not shading below the line. Because the y is negative, we're going to do the exact opposite. So we're going to shade above this line. Now, if that's difficult to remember, you can always transfer this line into slope-intercept form and graph using that slope-intercept form method. But we are shading above the line. Okay, in this problem, you cannot use the intercept method because you're only going to get 1 point. So we have to put into slope-intercept form. So I'm going to move my x over to the right, and I'll have y is greater than -x plus 0. So our m is equal to -1 and our b is equal to 0. So there's our y-intercept, and we're going to go down 1 and run 1. This is like a 1 over 1. This is going to be a dashed line because there's no equal sign. So it looks like that. And this time we are shading above because that's a greater than. See? We're shading above. And so we'll shade over here. Number 17 is already in slope-intercept form. So our m is 1, which is like a 1 over 1, and our b is 0. So we'll start at 0 and we'll rise 1 and 1 run. There's no equal sign, so this is dashed line. And it's less than, so we're going to shade the portion below the line. Remember, never think of shading left or right unless it's a completely vertical line in the form x equals something. So we always think of shading above or below. Okay, number 21, we have 2x minus y is greater than or equal to 2. So we move the 2x over, and we have -y is greater than or equal to negative 2x plus 2. And then we're going to divide by negative 1. Remember, when you divide by a negative number, the inequality is going to flip directions. So we'll get y is less than or equal to a positive 2x minus 2. So here's our y-intercept, negative 2. And we're going to, this is like a 2 over 1, so we'll rise 2 and run 1. And it's going to be a solid line because of the equal sign. So using a straight edge, which I don't have, we're going to do something like this. Okay? All right. Now, for the y is less than 4, there is no slope, so we have 1, 2, 3, 4, and this is going to be a dashed line, and it's going to be completely horizontal. Okay, now I'm shading below this line, and I'm shading below this line because they're both less thans. So the portion that's below both of them is this portion right here. So there's the shading for this one. Okay, when we solve this, we take the absolute value of x, or we take the x out of the absolute value and leave the inequality and the number after it alone. And then we go back and we take it out of the absolute value and we flip the direction of the inequality and the 3 to a negative 3. So when I graph this, I'm graphing x is greater than or equal to 3, which is a solid vertical line like this, shading to the right, the greater than side. And then when I shade this one, this is a solid vertical line at x is equal to negative 3, but it's less than, so I'm shading to the less than side. So this is a compound inequality. Okay, we've got x minus y is greater than or equal to 1, so I'm going to move my x over to the right, negative y. Actually, you know what? I'm just going to use the intercept method for this. So I have x is equal to 1, and I'll graph that there. Y is going to be equal to negative 1, so I'll graph that there. This is going to be a solid line. And I'm going to end up shading below this line because it's a greater, but my y value is negative. So I will shade below, but I'm going to shade in a moment. My next line, y is greater than or equal to 2. Now this is a horizontal line at y is equal to 2. So it's going to look like this. And it's a greater, so I'm going to be shading above. So I'll be shading below the first line, but above the second line is just that little portion in here that ends up being shaded. Okay, this first line I'm going to shade using the intercept method. So x is going to be 1. And y is going to be negative 1. It's going to be a solid line. And I'm going to be shading, now this is greater, but the y is negative, so I'm going to be shading below on this line. This is an OR. And the next line is y is greater than or equal to 2. So this is going to be a solid line, a horizontal line, at y is equal to 2. And I'm going to be shading above on this line. Now, this is an OR, so I'm shading everything, not just the intersecting portions. So I'm shading everything above this line. And I'm shading everything below this line. So all of that area gets shaded. Okay, for number 33, because 3 and 2 both go into 6, I'm going to use the intercept method. So the x-intercept, I have 3x is equal to 6, so x is equal to 2. And I have 2y is equal to 6, so y is equal to 3. This is a dashed line, and it's a less than, and the y is positive, so I'm just going over, I'm shading above this line. Now this is an OR, so I am going to be shading everything. Just to be able to see it better, I'll wait to shade the other one. This next one, because 1 and 2 go into this, I'm also going to use the intercept method. X is going to be equal to 2 when I eliminate the y. So that's that point there. And y is going to be, well, let's see, negative 2y is going to be equal to 2. So y is going to be equal to negative 1. And this is also a dashed line. So I'll dash it. This time the y is negative. This is a greater, so I normally shade above, but because I'm flipping that, I'm shading below. So I'm shading below this line, and I forgot to write this down, but we're shading below this line. And it is an OR, so we're shading everything. So let's start by shading below this line. We're shading everything, not just the intersecting portions. And we're shading below this line. So we're shading all of this stuff. If it was an AND, it would have been just this stuff in here, but we're shading everything. Page 236. Okay, when we solve absolute value inequality, we take the item out of the absolute value, and we leave the inequality and the number after it alone. And when we solve for this, we get y is less than 1. And so this is going to be a horizontal line, a dashed line, and it's going to be right here. Okay. Then I'm going to go back and I'm going to take it out of the inequality, and I'm going to flip the inequality and flip the number after it. And when I solve this, I get y is greater than negative 3. And so I put a horizontal line right here. Okay? And this is, we're shading above on this one, and we're shading below on this one. So we're shading just the intersecting portion. Oops, what did I just do? We're shading just the intersecting portion here. Okay, we take it out of the absolute value, x minus 2, and we leave the inequality and the number after it alone. We add the 2, and we get x is greater than or equal to 3. So this is a solid line. It's vertical at x is equal to 3 right here. And then we go back and we solve it again. We take it out of the absolute value, and we flip the inequality and the number after it. And then we add 2 to each side, and we get x is less than or equal to a positive 1. Okay, so that's there. So on this one, here we're shading to the right because it's greater. And so we're going to shade this area here. And this one we're shading to the left because it's less than. So we'll shade this area here. You know, when you have a greater, you know it's going to be a diverging area, so you're going to have two shaded regions. If that were a less than, we'd have a converging region where you'd have just a single shaded region, like on the previous problem. Page 247. Okay, in an ordered pair, like let's say 5, 2, this is called the independent variable. And this is the dependent. I didn't spell that right. Dependent. Oops, let me erase that. Dependent. Okay. So in other words, if I had something like y is equal to x plus 3, if I were to plug in a 2 here, I would pop out a 5. This y depends on what I decide to plug in here, which is why they call that x the independent variable. You choose that, and y then depends on that x. So this is the independent variable because we're only being asked what the first variable is. The definition of a function is a collection of ordered pairs that have unique domain values, meaning the domain values cannot be the same. The range values, the y values, can be the same, but the domain values cannot. So, for example, if I use these for my domain values here, and these for my range values, I could make a collection of ordered pairs like, say, -3, 4, 2, 4. So far, this is a function because even though I have the same range value, I do not have the same domain values. So I'm okay. But as soon as I do something like this, -3, say 6, this and this now are non-unique, and so this is not a function. The easy way to think of that is with the vertical line test. If I were to graph this, -3, 4 graphs over here, -3, 6 graphs there. If I put a vertical line, it would go through 2 of those points, and that tells me that this is not a function. But I didn't really need to graph it to see that if they have the same domain value, it's going to violate the vertical line test. Okay, a relation is a set of ordered pairs. The domain of a relation is the collection of all of the first component variables, or the x values. The range is the set of all the y values. And finally, a function is a collection of ordered pairs that all have unique domain values. Another way of saying that is a collection of ordered pairs where each domain element is paired with one and only one range element. A relation, we'll say a collection of ordered pairs is called a relation, where each domain value is paired with one and only one range value, or that each domain value is unique. The vertical line test is used to determine whether something is a function or not. If a vertical line only passes through the point, through the function one time, it is a function. So let's write that in words. A vertical line, if a vertical line will intersect the graph of a function well, let me say, stop with the if. A vertical line will intersect the graph of a function in at most one point. Number 5, we have all unique domain values, 5, 3, 4, and 7. So we really don't even need to check the range values. We do know that this is a function. Okay, here we have this. Okay, here we have a domain value of 2 being paired with a 4, and another non-unique domain value paired with a different 6. This is not a function. Okay, here we have all unique domain values. So this is a function. Okay, here we have non-unique domain values. Each of those domain values is paired with a different value. Here again, this is not a function. All right, in number 13, both of these, I take it back. On number 13, your domain values are the set 2, 5, 11, 17, and 3 in no particular order. The range values are 1, 7, and 20. This is a function because there is no one domain value that's being paired with more than one different range value. And so this is a function. All right, the domain here is equal to just 1. And the range, in no particular order, is 5, 2, -1, -4. And 1 is being paired with 5, here is being paired with a different value. 2, here is being paired with a different value. So this is not a function. Okay, the domain value, because this arrow is going forever to the left and forever to the right, the domain is equal to -infinity to infinity. The range, because this is forever going up and this is forever going down, is also -infinity to infinity. This is a function, and the easiest way to tell it is because you can use the vertical line test, and it shows that any single vertical line can only intersect at most in one place. So it is a function. All right, in this problem, the domain is -infinity to infinity because even though it's getting kind of slighter, this is forever going this way and this is forever going this way. The range is -infinity up to 4. And it looks like it's touching that 4, so I'm going to put a bracket on the 4. This is a function because it does pass the vertical line test. If I were to draw a vertical line at any one point, it can only cross it at most one point. Okay, here the domain is a little hard to see because it's blurry, but that's a 3. So the domain is going to go from 3 to infinity because it's going out that way for forever. And the range, even though it's ever so slight, it is increasing this way forever and this way forever. So the range is -infinity to infinity. If we were to put a vertical line through this, it's going to intersect in many places in more than one spot. So this is not a function. Okay, if we think of this as our x is our domain value, if I were to plug in, there's nothing that I can plug in that will generate more than one y value. So, in other words, for any single x value that I plug in, I'm not going to create more than one y value. So this is a function. Oops. This is our domain value. So there's no restriction on the inputs that I can supply. So my domain is negative infinity to infinity. This is a function because for any single x value that I put in, I can only get a single y value out. I'm not going to get two different y values for the same given input value of x. So this is a function. Okay, so this is our domain value. This is our range value. If I plugged in a -1 for y, I would get a +1 out here. If I plugged in a +1 for y, I would get a +1 here. This tells me that a single domain value will produce two different range values. So this is not a function. What is the domain? Well, no matter what I plug in here, this has to be from 0 to any positive number. So the domain for this is, let me erase that because I got to put a bracket. It's from 0 to infinity. I cannot be negative because there's a even exponent here, and that will never equal a negative number. So there's the domain. Number 27, this is our domain value. There's no restriction in what we could possibly put in for the domain. So the domain is negative infinity to infinity. And there is never going to be a single x value that you plug in that you would solve and get two different y values. Every single x value you put in will give you a single y value out. So this is a function. There is no restriction on any of the x values that we could put in. So the domain here is all real numbers. Okay? But an inequality is never a function. And the reason it's never a function is because this involves a shaded region. A shaded region represents a collection of dots. And if you put a vertical line, it'll cross in an infinite number of places. So this could never be a function. So not a function. Okay, because x has to at least be 0 or bigger, because we cannot take the square root of a negative number, the domain is 0 to infinity. But once you do plug in a domain value, you will never produce two different y values for any given one x value. So this is a function. Okay, in this problem, there's really almost no restriction on x, except x cannot be equal to 0. Because if x were 0, there is no y that exists that would have the product xy be equal to 1. So x could be anything but 0. The way we do show that in interval notation is we go from negative infinity all the way up to 0, but we don't include the 0. And then we union that with 0 to infinity. And again, we put a parenthesis so we don't include the 0. This is just a fancy way of putting this into interval notation. Okay, is this a function? Yes, because there is not any one given x that will produce two different y's. So this is a function. Okay, let's talk about the domain first. We know that 4x plus 2 has to be at least 0. So that's going to give us our domain. 4x now has to be greater than or equal to negative 2. So x is greater than or equal to negative 2/4 or negative 1/2. How do we write that in interval notation? Well, we go from -1/2 all the way up to infinity. That's the domain. Is this a function? Well, it is a function because there is no one single x that you could plug in that would produce two different y's. So it is a function. Okay, let's talk about the domain. In order to avoid having an undefined fraction, x minus 9 cannot be equal to 0. That tells us that x cannot be equal to 9. In order to write this in interval notation and find the domain, we go from -infinity all the way up to 9, but we don't include the 9. And then we union this with 9 to infinity, but again, we don't include the 9. So that's the domain. Is this a function? Yes, because there's no one x that you could plug in that would yield two different y's, so it is a function. Okay, part A. What are the possible values of the dependent variable? Well, the number of gallons depends on the hours. So possible values go from 0 to 4,000. Well, 0 to 3,000 because it doesn't ever get higher. Okay, part A, the dependent variable is like the y-axis. So those are gallons. And it's going from 0 to 3,000. So the possible values go from 0 to 3,000, including those. So we'll put brackets. Part B, for how long is the water level increasing? Well, that's just this portion right here. So it goes from 0 to 25 hours. So 25 hours. How long is it decreasing? Well, that's here. 50 to 75 hours is also 25 hours. Part C, how many gallons are in the pool after 90 hours? Well, here's 90 hours, so that's 2,000 gallons. And finally, part D says, call this function g. What is g of 0? Well, g of 0 is 0. What does it mean in this example? Well, it just means that there are 0 gallons of pool at the 0th hour. In other words, before you start filling in any water, you start with 0 gallons in the pool. Okay, number 41, fill in the blanks. You could do something like the cost of gasoline depends on the number of gallons purchased. So we could say the number of the cost is a function of the number of gallons. Okay, f of x is -3x plus 4. So f of 0 is -3 times 0 plus 4, which is simply 4. So f of 0 is 4. Okay, g of x is the function shown. So g of -2 is -2 squared plus 4 times -2 plus 1. This becomes negative. This will become a positive 4. That's squared. Positive 4 times -2 is a -8 plus 1. So this becomes, see, this negative is that one there, but this became a positive 4. So this becomes -12 plus 1, which is -11. All right, f of p, you just replace p everywhere you see an x. So f of p is simply -3p plus 4, and that's it. Okay, f of -x, we're just going to plug a -x in everywhere we see x. So this will be -3 times -x plus 4, which is going to be a positive 3x plus 4. Okay, everywhere we see x, we're going to plug in an x plus 2. So this is going to be -3x plus 2 plus 4, which will be negative 3x minus 6 plus 4, which will be negative 3x minus 2. Okay, now everywhere where we see an x, we're going to replace it with p over 3. So we replace that there and there. So this is going to be a negative p over 3 squared plus 4 times p over 3 plus 1. Well, this is going to be a negative p squared over 9 plus 4/3 p, or 4p over 3, plus 1. And now to kind of clean it up and put it in a more a form where you can see the coefficients a little easier, I'm going to make this negative 1/9 p squared plus 4/3 p plus 1. So that's g of p over 3. Okay, we're trying to find f of 2. So where we look for the x value of 2, and now we pop out the y value. So this is equal to 2. That was part A. For part B, we're looking for f of negative 1. So we look for the negative 1, and then we pop out the y value, which is 3. So this is 3. Okay, part A wants f of 2. So we look for the x value of 2, and it's popping out of 15. So this is 15. For part B, it wants f of negative 1. So we look at the negative 1, and it's popping out of 10. So f of negative 1 is 10. Okay, here, part A, f of 2. Our x value is 2, so we go out to the x at 2, and then we pop out the y value. The y value of this is 3, so f of 2 is 3. For part B, they want f of negative 1. So we go out to negative 1, and the y value at negative 1 looks like it's right there, which is 1, 2, 3, negative 3. So f of negative 1 is negative 3. Okay, the equation 2x plus y, that's a linear equation, so it has a straight line as its graph. One point that lies on the graph is 3. Well, if you plugged in a 3 here, you would have 6 plus y equals 4. So y would be equal to negative 2. And then it says, if we solve the equation, use the function notation, we have a linear function because it's a straight line. And it's being defined as f of x, that you can think of as your y. So if we move this over to solve, we would get negative 2x plus 4 for this function. F of 3, well, we would replace a 3 here, and we would get negative 2 times 3 plus 4, which is negative 6 plus 4. So f of 3 would be negative 2, meaning that the point 3, negative 2 lies on the graph of the function. Okay, so the first thing we're going to do is solve this for y. So we bring our x over there, and we say 3y is equal to negative x plus 12, and then we divide by 3, and we say y is equal to negative 1/3 x plus 4. So part A, we're going to transfer this into function notation and say f of x is equal to, actually this was part A, this is part B. So f of x is equal to negative 1/3 x plus 4, that's part B, that's function notation. In part C, we want to find f of 0. Well, that's negative 1/3 times 0 plus 4, which is 4. So f of 0 is equal to 4. Number 65, we're going to start by solving for y. So we have y is equal to negative 2x squared plus 3. Now that's part A. Part B is changing this into function notation. So we simply replace the y with f of x. And part C is we want to find f of 3. Well, that's negative 2 times 3 squared plus 3, or negative 2 times 9 plus 3, which is negative 18 plus 3, which is negative 15. Okay, so for part A, we're going to solve for y. Bring the 4x over, so negative 3y is equal to negative 4x plus 8. We'll divide by negative 3. So part A is y is equal to a positive 4/3 x minus 8/3. Part B will replace that f of x with y. And part C, f of 0 is equal to 4/3 times 0 minus 8/3, which is, well, I'm sorry, we're finding f of 3. Why am I plugging in f of 3? Is this is going to be, this will cancel, so we'll have 4 minus 8/3. So let's make a fraction. So this is going to be 12/3 minus 8/3, which will be 4/3. So that's f of 3. Okay, here we have f of x, which we can think of as y, equals negative 2x plus 5. So we'll put 1, 2, 3, 4, 5. That's our y-intercept. Our slope is negative 2 over 1, so we go down 2 and run 1, and we draw our line. Okay, so now it wants us to find, or give us the domain and the range. So the domain of this problem is negative infinity to infinity, because it's going out this way for forever and this way for forever. And the range of this function is negative infinity to infinity, because it's going up for forever and also down for forever. Okay, here's our y-intercept. Here's our slope, rise 1, run 2, and we draw our line. And the domain is negative infinity to infinity, because it's going left and right for forever. And the range is also negative infinity to infinity, because it's going up forever and down forever. Okay, y is equal to negative 4, 1, 2, 3, 4. This is a solid line like this. Okay, the domain is negative infinity to infinity, because it's going left, right, and left forever. But the range is simply equal to negative 4. Okay, if this taxi cab driver is charging $2.50 per mile, then 0 times 250 is 0. 1 times 250 is 250. 2 times that is $5. 3 times that is $7.50. The linear function that gives a rule for the amount charged is 2.5x. Graph this function for the domain 1, 2, and 3. So I'm just going to put this in the first quadrant, because none of our values fall outside of that. And 0, 0 is here. Let's do a 1, a 2, a 3. We'll do 250, 5, and 750. So 1 and 250 is there, 2 and $5 is there, 3 and 750 is there, and we graph this and it looks like this. Okay, for a femur of 56 centimeters, h of 56 would be equal to 69.09 plus 2.24r, which is 56. This is 69.09 plus, let's grab a calculator. 125.44, which is 194.53 centimeters. Okay, number 78. They want a tibia measure of a height of a man with a tibia of 40 centimeters. So h of t is what we're after. Height of a man, actually. So h of 40 would be equal to 81.69 plus 2.39 times 40. And you can do the math on this, but it's going to come out to 177.29 centimeters. Okay, number 79, they want the height of a woman with a femur of 50 centimeters. So this is the femur here. So they want h of r for the woman, and they want it to be 50 centimeters. So h of 50 would be 61.41 plus 2.32 times 50, and you can do the math, but this should come out to 177.41 centimeters. Okay, and finally, number 80, they want a height of a woman with a tibia of 36, so this is what they're after. They're after h of t there, and they want h of 36. So this is 72.57 plus 2.53 times 36. And again, you can do the math, but this comes out to 163.65 centimeters.